Okay, so in this video we're going to complete the M step for our missing data problem. So in the previous video we calculated the joint log likelihood, where y is our data that we've observed and z contains our missing input. And we realised that this is going to, when we take the expectation of our joint log likelihood with respect to z, we're going to have to know how to evaluate the expected value of z and the expected value of z squared. So that's as far as we got. So now we're going to complete the M step, the maximisation step. So what that would involve is taking the joint log likelihood, calculating its expected value with respect to Zm, and then we differentiate it with respect to theta to find out what our theta I plus 1 should be, so our next best guess at theta. So what I'm going to do is, actually it's slightly easier if we reverse the order. So if we just write this as log p from now on, so we don't have to write out all this stuff. And this expectation, I'm just going to write it just as e, so we don't have to write out all this stuff. So usually, what we've done before is we said we'd find the expected value of log p, and then we're going to, we'll differentiate that with respect to theta, and then set the thing equal to 0. And actually, we'll just do it the other way around in this case. So that's the same as taking the expected value of the differential of log p and setting that equal to 0. And it's just because the notation is slightly easier, basically. Okay, so we have our log p here, and we're going to start off by just expanding out this stuff. And we know we're going to differentiate with respect to theta, so we only need to keep things that are a function of theta. Everything else is going to get absorbed into this constant, which will then disappear when we differentiate. So this log p, our joint log likelihood, is equal to our, so we start this summation for n is not equal to m. That's fine. Now all this, actually, these two Gaussian distributions, they both have the same variance. So actually what I'm going to do is, it means we know that there's going to be a minus 1 over 2 sigma squared outside of everything we write in here. Now we can say, right, it's a summation of n is not equal to m. And we have a Gaussian with the argument is yn, the mean is this thing, and the variance is this thing. So we have our argument is yn, and it's minus theta transposed xn, and that's all squared. So that's fine. And then we've got this here. So what I'm going to do actually to make our life a bit easier is, if we, let's say we define a new vector called u, which is equal to xm zm, then it means we can write this, we can write it simply as, let's call that a um. We can write this expression just as theta transposed just to make the notation a bit easier. So we end up with adding, okay, so what do we have? We have ym is the argument, and then the mean is now theta transposed that's also squared. Right, now we're going to expand these brackets, and we're going to say this is still equal to a constant, and anything that's not a function of theta is going to be absorbed into that constant. So we still have our minus 1 over 2 sigma squared, that's fine. And with our summation for n is not equal to m. Okay, so we're going to expand this. Well, there's going to be a yn squared, but that gets absorbed into the constant. we are going to have a minus 2 yn theta transposed xn is going to be in there. And we're also going to have a theta transposed xn squared, but we're going to write that out in a way that lets us relate back to some previous expressions relating to taking the derivatives of vectors. So what I'm going to do is write that as theta transposed xn multiplied by xn transpose theta, okay, which is the same as that thing squared. And then we've got all the same tricks applied to expand this bracket here. So we're going to have a minus 2ym, another theta transposed, and this time a plus theta transposed transposed theta. So same tricks. Plus a constant. Okay, so this is, we'll say this is log p. Now what we're going to do is differentiate log p with respect to theta. So we're still going to have this this constant at the front, which I'll try and copy. Yeah. Then we, like I say, in the videos leading up to this one, we've seen how the expressions we kind of rely on to differentiate these types of things with respect to vectors. So we won't go into it in too much detail, but we still have our summation for n is not equal to m. We're going to take the derivative of this with respect to theta. What you end up with is minus 2 yn times the vector xn, and then when we look at this expression, and when you take the derivative of this with respect to theta, you end up with this matrix transposed plus this matrix, and all that's multiplied by the vector theta. And this matrix is actually symmetrical, so that's the same as saying the differential of this with respect to theta ends up being 2 times xn transpose times theta. And then, so I should use the same sort of brackets. And then all the same tricks apply to this stuff over here. So we have a minus 2, it'll be a ym plus 2, and then that matrix transposed, all multiplied by theta. And our constant has disappeared because we've taken the differential. Okay, so that means now if we take the expected value, so we're going to look at the expected delta log p, delta theta, and remembering this is with respect to z, and u actually contains z, so all this stuff is going to be unchanged, but we are going to need that, so we'll need to look at that. So we're going to end up with still a minus 1 over 2 sigma squared. Then all of this is the same. But then on the right hand side now we have minus 2 ym, and now we have our expected plus 2, and now our expected transposed. And so this is where this is going to contain our expected z's, and this is going to contain, we'll see later, but you can probably see already, this will contain expected z's and expected z squared. Okay, so we set all of that equal to 0, and we solve for theta, and that theta is going to be our theta I plus 1. It's going to be our next best guess. So we can save a bit of room. So we can remove that. So setting this expression equal to 0 implies that. Okay, so we can remove that thing. So in fact, I'll drag it down. Okay, so we can get rid of this straight away. And then everything here has been multiplied by 2, so we can get rid of all those 2's as well. Right, so just squish everything up. Now we're going to collect together all the terms that are a function of theta and everything else that's left behind. So multiplied by theta, what we've got is our summation for n not equal to m of xn transposed. So that's here, and then we've also got this expected so add expected um transposed, as they will be multiplied by theta, and then we have a load of stuff that's left over. So we have a minus ym expected value of and then we also have this thing here as well. So we have a minus, and then we've got a summation for all the other n's multiplied by xn, and that's equal to 0. So now we can just solve for theta. So we're just going to move all this stuff over onto the right hand side, and then pre-multiply by this thing, the inverse of that thing, sorry. So it means, therefore, what we end up with is the inverse of this matrix multiplied by, we're going to have all this stuff, added to, so the only thing left over is here. So ym expected value of and what I should have written here, of course, is that that's what our theta is now. So our next best guess at theta, our theta I plus 1 is equal to all of that stuff. Okay, and that is our m step. So I should say, just to be clear, we have to remember that our so that was equal to xm that we knew, and zm was our missing data point. So when we look at use different color, when we look at this thing, we're actually looking at the expected value of, okay, so we're going to have a squared then xm zm, same down here, xm zm, and then a zm squared. So that's where we're going to need our first order kind of term that we found in the previous video, so our expected zm. This is where we'll need our expected zm squared. And then obviously here we've got the expected value of just xm and zm. So this is our, again, this is our kind of first order term that we found in the last video. Okay, so that is about it. So we've written down our E step here. Then we can delete all that stuff. And then that is our M step. So once you've been through all the maths, implementing this thing is actually relatively easy. So okay, well, your E step, you just need to calculate these quantities, and then when you do the N step, you just set theta I plus 1 equal to this expression here, where it's in these here and here. That's where our kind of expected Z's appear. And that's it.